which is generation of, right? You can see the screen, right? Just see if the screen is visible.
No, ma'am.
Okay, right? I hope now it is visible. Hmm? So see, last class we had done with generation of high frequency, high AC voltages, in which we had done with the Tesla coil circuit. Okay. So today I'll explain you the next part, which is generation of impulse voltages. Okay. Now, any idea what is meant by impulse voltage? Any idea what is meant by impulse voltage? Yes. What do you mean by impulse voltage? Have you ever heard about impulse voltage? Okay. Okay. Let me give you an introduction to what is meant by impulse voltage. Okay. So standard impulse wave shapes. What are your standard impulse wave shapes and what is meant by standard impulse voltage? Okay. See, you all are aware of lightning impulses. Okay. Lightning, you all are aware of lightning. Correct?
Yes, ma'am.
Huh? So, see, in TD we had studied that if your lightning strikes the wire, okay, the transmission wire, you have the waves, waves induced in the power cable. Okay, these waves are nothing but as soon as the lightning wave strikes, okay, you have some disturbing waves generated. Okay, these disturbances can travel up to the endpoints, okay, where you have the location of transformer and damage the transformer and the end accessories, right? Because of which we provide the what we provide to protect our transformers and end accessories in the transmission line. Yes. If you remember, we had used the lightning arresters or surge arresters. Okay, these are to protect our transmission lines and the power cables and the end accessories. Okay, so this standard, what is this standard impulse wave is? These are the transient over voltages. Okay, impulse waves are the transient over voltages due to and switching surges, lightning and switching surges, okay, which cause buildup of voltage in the transmission lines as we had done in the TD, okay, and other electrical apparatus. I told you the devices which are connected to the transmission line, okay. So see, the lighting over voltage wave can be represented as double exponential waves. Okay, see, it means what? When the experimental study was done on what exactly the, see, in TD we had seen you have a tower, okay, and here you had the power cables. Okay, if suddenly the lightning strikes, okay, our regular wave, power wave was going this way. Okay, now suddenly, when the lightning strikes, what happens? This gets disturbed and you have the generation of high frequency wave. Okay, now an experimental study was done on to understand what are the shapes, what would be the probable shape of this surge which is generated due to either lighting or due to continuous switching, okay, switching of load. Okay, an experimental study was done. Okay, in that it was seen that it is having a certain wave shape. Okay, the wave shape of this was seen to be like this. Okay, where it had some front portion. Okay, this was the front portion and there was a tail portion. Okay, there was a tail portion. Okay, so this these were expressed using an equation, okay, of a double exponential wave. Okay, these were the double exponential wave and represented like this, where you have two exponentials. Is it clear up till here?
Ma'am, ma'am,
Yes.
ma'am, allow Priya, ma'am.
Okay, was it clear up till here what I said? Up till here, was it clear what I said? Was it understood up till here, Siri?
Ma'am,
Yes,
alpha
ma'am.
and beta.
And that I'll define now. These are your constants, alpha and beta. These will define it now. Okay. But for the time being, this was found to be the equation which is having two exponentials. Okay. But what is meant by impulse wave, is that understood now?
Yes, ma'am.
Yes, ma'am.
Okay, now see, where alpha and b are constants of microsecond values. Okay, these are your constants of microsecond values. Okay, so the above equation represents a unidirectional wave. Okay, so as said by Ashwini, okay, this is a unidirectional wave, okay, which usually has a rapid rise to peak value. Okay, I showed you a waveform. Okay, I showed you a waveform which was like this. So it is said that it is having an exponential rise to peak value. See, this is rise to, this is your peak. Okay, rise to peak value and a very slow fall time. Okay, so fall time may go to 0. Okay, so standard impulse wave shapes are specified by defining their rise of the front time, okay, fall or the tail time to 50% of peak value and the value of the peak voltage. Okay, so see, first you see this. Okay, so this was your standard impulse wave. Okay, you can see here it is coming from your, okay, extending up till point A, which is your peak value, and then it is reducing. Okay, it may go beyond point B also, but here we have limited it to point B. Okay, so see, standard impulse wave shapes are specified by defining the rise or the front time. Okay, so see, this part is called, okay, see, the peak value A is fixed and is referred to as 100% of value. Okay, so this A is your peak value. Okay, next, the points corresponding to 10% and 90% of the peak values are located in the front portion. What do you mean by front portion? It is, see, up till point A, right, up till this point, this is called as wave front. Okay, this is called as wave front. Okay, this part is wave front and this part after A is your wave tail. Okay, so any impulse wave is specified in terms of its, see here it is written, in terms of its rise time or front time. Okay, it means how much is the time taken for the wave to rise from 0 to the peak value is your front time or rise time. Okay, then fall time or time to 50% of peak value. Okay, from here to here up till point E, what is the time taken? Okay, and the value of the peak voltage. It means here what is the value. Okay, so see here, thus if you have been given as 1.2 by 50 microsecond 1000 kilovolt wave. Okay, it means what? 1.2 is your front time. It means a wave of 100 kilovolt is requiring 1.2 microseconds to rise from 0 to point A, and at point A it is having the value of 1000 kilovolt. However, see here 50 microsecond is there. However, it is taking 50 microseconds for the wave to fall from A to point E. Is that understood? Yes, is that understood?
Yes, ma'am.
Right, so there are three parameters when you specify an impulse wave. One is its rise time. Okay, one is its rise time. It means, sorry, just a minute. One is its rise time, which is 1.2 microseconds. Okay, which is the time taken by the wave to rise from 0 to peak value. Okay, next is the fall time, which is the time to 50% of peak value. It means from here to point E. Okay, and the magnitude, what is the maximum value of the voltage? It means 1000 kilovolts. Okay, so a standard impulse wave is specified according to BIS standards to be 1.2 by 50 microsecond wave. Is that understood up till here?
Yes, ma'am.
Okay, right. So we'll now go on defining what is this T1, T2, T3 and all. Okay, so see, the peak value A is fixed and is referred to as 100% of the value. Okay, so your point A is your peak value. Next, the points corresponding to 10 and 90% of the peak values are located in the front portion. Okay, I told you what is the front portion. From 0 to A is your wave front. Okay, so point C is 10% of the wave front. Point D is the 90% of the wave front. Okay, now the line joining these points is extended to cut the time axis of O1. Okay, it means what? You draw C, you have to mark C. First you have to draw a point C which is 10%, okay, of the peak value, and here you have to draw a point D which is 90% of the peak value. Okay, so when you are, see, it's starting from here. Okay, impulse wave is starting from here and going to this. So you have to draw a tangent. Okay, this line which is joining points C and D. Okay, the line where it cuts the axis. Okay, this line which cuts the axis, x axis or time axis, is your point O1. Okay, and this point O1 is taken as the virtual origin. Okay, it is not the original origin. Original origin is here. Okay, O1 is virtual origin. Is this understood up till here? Right?
Yes, ma'am.
Oh, okay. Right? Now, okay, so 1.25 times the interval between the times T1 and T2. Okay, where are my T1 and T2? See, T1 is the time of 10% of peak value, that is point C, and T2 is the time of 90% value, okay, at point D. So this is your T1 and T2. So 1.25 times the interval between T1 and T2. corresponding to points C and D, okay, is defined as the front time. Okay, so your front time is 1.25 into O1 T2 minus O1 T1. Is it understood up till here? Yes? Soumya?
Ma'am, 1.25 I mean.
That is fixed. This is a constant. This is experimental determination. Okay, so from experiments, it is determined that 1.25 times this is your wavefront. See, till now what I said, the wavefront is from here to here. Okay, theoretically it is from here to here, from O to A. Okay, from here to here is your wavefront. I told you, right? This is your wavefront. Okay, it means front of the wave, the face of the wave. Okay, but now since you join C and D and you get a virtual origin. Okay, you get a virtual origin. Okay, now we do not consider this origin. We are considering this origin. So this times, okay, 1.25 times of this is your wave front time. It means what? It does not start from here. Okay, it is starting from somewhere here. Your wave is starting somewhere from here. Understood that?
Yes, ma'am.
It's only because of this virtual origin. Okay. So it is 1.25 O1 T2 minus O1 T1. This is called as your front time. Okay, this is your wave front, which according to BIS standards is 1.2 microseconds. Is it clear up till here?
Yes, ma'am.
Okay. Now you can see the point E. Okay, so this point E, see, this point E is located at what? 50% of the peak value. Okay, so this point E corresponds on the wave tail to 50% of the peak value, and its projection on the time axis is T4. See, after this we have our wave tail. Okay, we have our wave tail. So E is the point corresponding to 50% of the peak value, whose projection on the time axis is defined as T4. Okay, understood this line? This statement is clear? Now O1 T4 is defined as the fall or the tail time. Okay, O1 T4. Okay, see, so O1 and T4 is defined, okay, this is defined as the fall time or the tail time. Now here the tolerances which are permitted according to the standards, right? For the wave front it is plus or minus 30%, right? Wave front time was what? 1.2 microseconds. Okay, 1.2 microseconds ka plus or minus 30% in the wave front is permissible. However, 20% is permissible in wave tail time, which is 50 microseconds. Okay, up till here was it understood? See, here it is written, Indian standard specifications define 1 by 2 by 50 microseconds wave to be the standard lightning impulse wave. Okay, it means in practical power systems, when you see a lightning impulse striking a power cable, right, it is said to have the wave shape of front time of 1.2 microseconds and tail time of 50 microseconds. Is it clear up till here? Is it understood up till here?
Yes, ma'am.
Yes, ma'am.
Okay, and the tolerance is allowed in the peak value. Okay, I gave you an example of 1000 kilovolts. I gave you example of a wave of 1000 kilovolt value, right? So the percentage tolerance allowed in the peak value is plus or minus 3%. Okay, so this is all about the standard impulse wave, which looks like this. Okay, and is specified in terms of its front time, tail time, and the peak value. Okay, up till here, is that understood? Okay, I hope up till here it was clear. Okay, Nihal? Nihal,
Yes, ma'am.
understood up till here?
Yes, ma'am.
Okay, right? So we now see, when we study this, okay, we understand that there is a impulse wave, okay, there is a lightning which is going to strike, okay, the power cables. So the power cables which needs to be installed outdoor has to be initially tested in the labs. Okay, now to initially test these power cables in the labs, you need to subject those power cables to such type of uh, impulses. Okay, so there has to be the circuits in the lab which can provide such impulse waves. Okay, so now we'll go, or we'll see which are the circuits that produce the impulse waves. Okay, so a double exponential waveform, okay, as mentioned in the equation. Okay, I told you this is a double exponential waveform. Okay, so see, you can see two exponentials, e raised to minus alpha t and e raised to minus beta t. Okay, so a double exponential waveform may be produced in the laboratory with a combination of series RLC circuit, okay, under over damped conditions, or by the combination of two RC circuits. So basically there are four different circuits, okay, which can produce the impulse waves. Okay, there are four different circuits which can produce the impulse waves. Okay, now we have to analyze these circuits one by one and calculate the value of the constants alpha and beta. Okay, so what I'll do is I'll give you the analysis for circuit A. You have to carry out the similar analysis for B. See, B and D are same. Okay, B and D are same, and C. Okay, I'll explain you the analysis for A. B, C and D you have to do. Okay, is that understood? Right, that would be working as your assignment. Okay, so we'll go ahead for the analysis of circuit A. Okay, see here. Now, this circuit, right? See, you already know this. You apply a KVL here, right? When you apply a KVL, what happens? See, the current through the load resistor R. It has to be the current, right? We have to calculate the current I. Okay, to calculate the current I start from applying KVL. So see, what is the voltage drop across this? How you give the voltage drop across the capacitor? Voltage drop across capacitor.
V naught, ma'am.
In terms of capacitance and current, if you have a capacitor, if you have a capacitor of capacitance C and current I is flowing through this, how do you give the voltage drop across this?
XC by omega.
Now it's a, okay, tell me. वोल्टेज ड्रॉप क्या होता है? V इज
Q
इक्वल
by
टू
C. Q by C, ma'am.
क्यू नहीं है रे इधर पिक्चर में. सी V is equal
नहीं.
to I X, okay, or IR if R is there. Now in terms of capacitance, how we write? 1 V is equal to 1 by C integration I dt. Okay, this is the voltage drop across the capacitor. You all know this, or some I'm talking something alien thing here? पढ़ा है ना ये?
Yes, ma'am. Yes, ma'am.
ठीक है. Okay, so voltage drop across capacitor is 1 by C integration I into dt. Okay, next voltage drop across inductor.
L
di
di.
by
Yeah, man.
Yes, correct. L di by dt. And voltage drop across resistor is R into I. It's
IR.
simple. Okay, here the I. So see, V is equal to 1 by C I dt integration over 0 to t plus Ri plus L into di by dt. Okay, now since see, you can see a spark gap here. Do you know what is meant by spark gap? Do you know what is meant by spark gap or spear gap?
No, ma'am.
You don't know? Okay, you can recall the initial classes where I had shown you the lab, high voltage lab. There were two electrodes, and in between we were testing the insulation of the air, which is acting as a resistance.
Yes, ma'am.
That itself is a spear gap or spark gap. Okay, where you have two electrodes. Okay, this is electrode 1 and this is electrode 2. Okay, you have two electrodes and in between there is a gap. Okay, this is called as a spark gap or a spear gap. Okay, so this is, see this, now if you see the circuit is open, it means there is no flow of current. See, why this equation will come into picture? This equation will come into picture only if the circuit is closed. Correct? Now, but the circuit is open here. Then how did I write this equation? See, this equation or this, see, one thing is you can write the equation, right, to find what is the flow of current only when the circuit is closed. Now, in such type of circuits, what we do is we give sufficient high voltage such that the gap between two electrodes become conductive. Okay, and it forms a closed path. So this is the case when you have the current flowing through the gap and completing the circuit. Okay, so with this, see, with the initial condition, see, when t is equal to 0, at 0 time when your gap was not conducting, here when your gap was not conducting, what happened? The circuit was open and there was no flow of current. See, being I of 0 equal to 0 and the net charge in the circuit Q is equal to 0. Okay, Q goes to 0 when your gap was not conducting. Okay, now writing the above equation, okay, whatever we have written the equation, I'll take the Laplace transform of it. Okay, this equation is what now? This is not at t is equal to 0. Okay, this is the equation at t is equal to 0. Yes, initial conditions, network analysis.
Yes, ma'am.
T is equal to 0 plus. This is the condition. This is the equation you get at t is equal to 0 plus. Okay. So, I'll take the Laplace transform of this equation. Okay. So, it is V by S equals to 1 by Cs into I of S plus R into I of S plus L into S into I of S. Okay, from this I get the equation for current flowing in the circuit, which is V by L into 1 divided by S square plus Rs by L plus 1 by LC. Okay, so the output voltage across the resistor R, okay, here is my resistor R. See, here is my resistor R. So the voltage across this is your V naught of T. So इसका भी Laplace transform I'll take, which is V naught of S. Okay, so V naught of S is equal to I of S into R. Okay, I of S I have already done here. So to calculate V naught of S, see what I have done. I of S I have taken, I of S I have taken, I multiply this with R. Okay, so I get VR by L into 1 by this thing. Up till here, was it understood?
Yes, ma'am.
Okay, now we have to find the roots of this equation. Okay, so the roots of this equation are the constants which we were talking, alpha and beta. Okay, alpha and beta are the roots of this equation. So how do you find the roots of this equation? Second order differential equation. Right? It's not differential. Okay. See, how do you find a? You have the a square. Yes. See, this is a quadratic equation of order 2. How do you find the roots? A and B. याद है नहीं है? Remember minus B plus or minus square root of?
Yes, ma'am.
हाँ
4AC
हाँ minus
divided
B
by
square divided by
2A.
2A. Okay, so इसका equation का the roots of this equation would be, right, roots of this equation would be, see, minus B, right, finally you get alpha and beta. When you, okay, you try to solve this equation, this formula you know, I have directly written alpha and beta. You try to get this. Is that okay?
Yes, ma'am.
See, this is a second order quadratic equation. You know how to find the roots of this equation. You apply that formula, you will get alpha and beta in this way. You have to solve such that you will get this. Is that clear up till here? Right? Now the same thing I'll apply to get the equation for, see, this was your V naught of S. Now I'll put this same here to get V naught of T. Okay, I'll apply this to get V naught of T. Okay, so it is V into or VR by 2L, okay, divided by square root of R square by 4L square minus 1 by LC e raised to minus alpha T minus e raised to minus beta T. Alpha and beta we have already calculated. Okay, alpha and beta we have already calculated. Okay, so when you see, do you all have notebooks with you?
Yes, ma'am.
You all are trying this. Okay, what I'll do after the class, I'll share the PPT with you. Okay, you try solving this. Okay, now see, V naught of T is equal to this much into this. Okay, so in next equation, what I'll do, I'll replace this by capital V naught. Okay, it means where your V naught is, see, I have replaced this by V naught. Okay, I have replaced this by V naught. Okay, so V naught is VR by 2L. V naught is VR by 2L divided by square root of R square by 4L square minus 1 by LC. Okay, this is your V naught. Okay, from this, okay, see, I have here the equations I have. I know what is alpha, I know what is beta. Okay, so when you have to see what you do, you calculate what is the sum of the roots alpha plus beta, and also you calculate what is the product of the roots alpha and beta, and tell me. Yes, tell me what is alpha plus beta. What do you get alpha plus beta?
R by L, ma'am.
फिर से करो. Check for this. Soumya, check your calculation somewhere. Yes, Hina, correct. Minus R by 12. Okay, Hina, you are correct. Now, let me know alpha beta, product of the roots. Product of the roots. Check for this. 1 by LC.
Yes, ma'am.
Okay. So, from this products and sum, you have the values of, this you get it from these alpha and beta. Okay, so these are acting as constants to calculate wave tail and wave front times. Okay, I hope up till here it was understood.
Yes, ma'am.
Okay then, right? So what we'll do is, see, next topic here. Here what we did, we checked with the circuits which are used in the laboratories to generate the impulse waves, okay, of which I have given you the analysis for circuit A. Okay, now you can see here circuit B and D are same. Circuit B and D are similar. Only thing is you get an extra resistance R1. Okay, now what is the value of, what is the work of these resistors, inductors are, the front wave front and the wave tail times, okay, are controlled by changing the values of these R and L simultaneously. Okay, in this case, if I talk R and L, if I change the values of these simultaneously, okay, this is required to control the wave tail and wave front times. Okay, so you have to suitably select alpha and beta depending upon how much. See why we do this, so that we get a standard wave of 1 by 250, 1 by 2 by 50 microsecond wave. To get this wave, I have to properly tune these parameters R, L and C. Okay, so that is why, see, C का तो ठीक है. Okay, with a given generator, capacitance C will be there. Okay, you have to choose suitable value for L, okay, and R, so that you get this wave shape. Okay, so what analysis we have done is for circuit A. Okay, you have to go for circuit B, D and C analysis. Okay, it won't be difficult because B and D circuit are similar. Okay, only one analysis will come. Only thing is circuit C is bit different, so you will have to be doing with two analysis, one analysis for circuits BD, one analysis for circuit C. Okay, that can be done. ठीक है, कुछ नहीं है, KVL अप्लाई करना है. You know, initially no current is flowing, but at t is equal to 0 plus, when the gap starts conducting, you have the flow of current. Okay, then you have to start with the analysis. Okay, am I clear?
Yes, ma'am.
I'll give you a Google class code. You please solve for those circuits and put up in the Google class. Okay, and the next part comes here is the multi-stage impulse generator circuit. Okay, so these, see, whenever we have the derivations for that thing, I'll take the classes online. Okay, right? Otherwise, is it okay with you people if I put the videos for this multi-stage impulse generator circuit and the circuits which are already defined?
Okay, ma'am.
You just go through the videos, right? And weekly, once or twice, we will have the live class so that I can clear your doubts on the videos. That would work out, right?
Yes, ma'am.
Okay, then, right? You all can quit the class.